In Lewis theory, we represent valence electrons with dots. And so we draw things called Lewis structures or dot structures. And we learned in the last chapter that valence electrons are very important. The valence electrons are kind of the outside of the atom, and that they are responsible for many of the chemical properties of atoms. And so in Lewis structure, we're looking at those valence electrons. And just to remind you, the number of valence electrons for the main group elements is the group number. So chlorine is in group 7A, it has 7 valence electrons. Calcium's in group 2A, it's got 2 valence electrons. The one exception there is helium. Helium is one of the baby brothers. He gets away with everything. So let's look at oxygen and review electron configuration. Let's do the electron configuration for oxygen. Well, how many valence electrons does oxygen have? How many electrons, sorry. How many electrons does oxygen have? It has 8. So electron configurations start out with the 1s subshell, and that's got 2 electrons in it. And next is 2s, and that's full, and then 2p. And we see on the periodic table that oxygen is in that p block, the second period, and it's 4 over. So this is 2p4. And then if we check, 2 plus 2 plus 4 equals 8 electrons. So this is the electron configuration of oxygen. How many valence electrons does oxygen have? 6. 4 plus 2. You just weren't finished. Oh. So it's got 6 valence electrons. So we're going to represent those as dots. And so the Lewis structure will just be the element symbol, which is oxygen. And then we're going to put dots around it, 6 dots. So 1, 2, 3, 4, 5, 6. Okay?
Do we always do that until it's filled?
Yeah, we will generally put them singly at first, top, bottom, right, and left, and then pair them up.
They wouldn't be opposite the two?
They could be.
Okay.
Exactly where you put them doesn't matter. So if you put them like this, that's equivalent. That's the same.
Okay.
What if you had those 2 single electrons together? Would be gone?
Yeah, we wouldn't do that. We wouldn't do this. Those are good questions. We wouldn't do that.
Thinking because this is this is a 2-dimensional analysis of it.
This is a flat representation. This is just our shorthand cartoon caricature of oxygen.
We don't do in that sense of putting them to the two side and the bottom and leaving it open. Is that because of that each orbital has to have at least 1 electron in its rotation?
It ends up having to do with the structure of the S&P orbitals, yeah.
Okay.
Because if we look at, in fact, let's do that. Let's look at the orbital diagram for oxygen. So there's 1s, and here's 2s, and here's the 2p. So 1, 2, 3, 4, 5, 6, 7, 8. There are 2 unpaired electrons. Okay, and so when we draw the dots, we don't do them in a circle. You're not going to, space them out evenly in a circle like they're playing Ring Around the Rosie or something. You're going to go top, bottom, right, and left, which is convenient on computers and stuff too. It also makes it very easy to look at it and see how many there are. When it's a circle, it's kind of hard to see, but like dice, you can look at it once you've reached a certain age. The 4-year-old can't. He still counts all the spots. It's pretty funny. But you can look at it and see, oh, that's 5. You can just see it. And when the dots are top, bottom, right, and left, you can look at it and see the number of dots without having to actually count them. But it also reflects the number of unpaired electrons that they have. Any questions? So each dot represents a valence electron. And when you're drawing them, on paper, make sure that you make them big enough that you can see them. We place the dots around the element symbol with a maximum of 2 per side. The exact location isn't critical, but we do put them by themselves first and then pair them up. And especially when you're doing the mastering chemistry homework, it's really important to follow that convention. So the one that I put the red X through, mastering chemistry won't like that one. It'll like the other two. Okay, and so you have to figure out what mastering chemistry wants. And atoms that have 8 valence electrons are unusually stable, and we learned that in the last chapter. That's why the noble gases are very unreactive, is they have 8 valence electrons. So when we look at a Lewis structure and see that it has 8 dots, we call that an octet. So just like in, choir, you can have a duet or a trio. You have an octet is 8 people singing. An octet of electrons is 8 electrons. And so 8 electrons is what the atoms are all trying to get. And again, we're only talking about valence electrons here. They're trying to get 8 valence electrons. So let's write Lewis structures for the first 10 elements, just because it'll be so much fun. Let's see here. So hydrogen. How many electrons does hydrogen have? It's got 1. So it's got 1 electron. Does it matter if you put it on the top, the bottom, the right, or the left? No. Just 1, you put it anywhere you want. Now helium has 2 electrons, and helium, we tend to pair those up. I don't know what mastering chemistry is going to do about that one. We don't often draw we don't often draw Lewis structures for helium because it doesn't bond with anything.
And that's because they're paired in the first,
Yeah, because helium only has 2 electrons. They're in the 1s orbital, and they are actually paired. So then lithium,
would that be paired in one single?
No,
I really-
Is it only one valence electron, so you only need one diagram?
yeah, beryllium has 2 valence electrons. They are paired though, but I think we ignore that.
Wait, lithium?
Lithium only has.
I'm sorry, lithium. Yes, I was getting ahead of myself. Lithium has 1 valence electron, so yeah, there's just the 1 there. Beryllium, we're going to do it like this, even though technically they are paired. Boron has 3. Carbon has 4. So we're going to put them around separately if we can. And then nitrogen has 5. So 1, 2, 3, 4. And then there has to be a pair somewhere. You can choose where you want to put the pair. It doesn't matter. But you're going to have 1 pair. Oxygen's going to have 6. 1, 2, 3, 4, 5, 6. Again, you decide where you want to put the pair. Fluorine has 7. I was just anticipating that I know there's going to be 1. And then neon, neon has 8. 8 valence electrons. And so it looks full, doesn't it? It's got 2 on the top, 2 on the bottom, 2 on the right, 2 on the left. It has arrived. It's got the octet, and that's what everybody's trying to get. Okay. Of course, atoms are not sentient beings, and so they're not trying to do anything, but it helps to personify them. I enjoy it anyway. Maybe you don't.
So when you have like O2 negative, is that like there's an extra 2 that are just thrown on top of those?
Yes.
Okay.
Mm-hmm.
Oh, they in the split theory, they did many objects, many.
Pardon me?
In the split theory, the carbon atom did many things of decision making where it decided to go through. So there is a quantum form of consciousness in that.
Maybe there is a quantum form of consciousness. The standard answer is that it's lower energy. But that's boring. Right?
I like quantum consciousness.
Yeah, quantum consciousness, yeah. So helium is stable with a duet of electrons. And hydrogen is a little guy also, and he's trying to get a duet of electrons. The others are trying to get 8, pretty much. Yeah. I'll tell you, we do lie to you in introductory chemistry.
So in Lewis
Sometimes
theory,
it's
we
hard.
don't do like negative and charged, like?
We're getting there.
We will? Okay.
Yeah, we're getting there.
So what happens when helium gives off an electron? Does that mean it just doesn't have any left?
Helium doesn't do that.
Or not helium, but hydrogen.
Yes, when hydrogen loses an electron to form a hydrogen ion, it doesn't have any electrons left. And so actually what it is a proton,
Just a proton.
just a proton. Yeah.
Isn't that neutral?
Well, some isotopes of hydrogen have 1 or 2 neutrons. Did you guys ever watch Hogan's Heroes?
Sounds familiar.
No? Okay.
Might have
Well,
been.
in World War II, have you ever heard of heavy water? Okay, heavy water is water that has deuterium or tritium isotopes in it instead of the protium, the normal hydrogen atom. And so deuterium has 1 neutron and 1 proton, and so it has a mass of 2. And tritium has 2 neutrons and 1 proton, and so it has a mass of 3. And so for hydrogen, those little differences are huge. But the predominant isotope of hydrogen is protium, which only has the 1 proton and no neutrons.
So can you drink heavy water?
Sure.
Won't make you sick or anything?
I don't think so, no.
What's the,
No, I don't think it'll kill you.
it's just heavier?
Well, it's heavier, yeah. It's heavier, and it's going to do different things if you're trying to do nuclear reactions with it.
Of course.
Yeah. So, in Lewis theory, the reason we're looking at Lewis theory is to talk about bonding. And so a chemical bond in Lewis theory involves either sharing valence electrons or transferring valence electrons for the atoms to get a stable octet of electrons. So ionic bonds involve transfer, where the metal gives its electrons to the nonmetal. And then the attraction there is that you have opposite charges that are attracted, not unlike magnets being attracted. In covalent bonds, the electrons are actually shared between the between the atoms. And then we have something we refer to as the octet rule. In chemical bonding, atoms are going to share or transfer electrons so that they obtain an octet of electrons. Okay, so that's just kind of the guiding force. And of course, there are exceptions to this. Hydrogen, lithium, and beryllium follow what's called the duet rule, because they're very small, and so they're just trying to get 2 electrons. Hydrogen couldn't handle 8 electrons. There's just no way. So he's just trying to get 2 electrons. And lithium and beryllium are also very small, and so they're also trying to get 2 valence electrons. So let's write Lewis structures for magnesium and for sulfur. So the Lewis structure starts with the element symbol. So magnesium. And then we look and we see how many valence electrons does magnesium have? 2. So I'm going to put a dot here and a dot there. So 2 valence electrons, there we have the structure for magnesium. How about sulfur? How many valence electrons does sulfur have? 6. So we're going to put 6 around, and 2 of them will be paired, and 2 of them, there will be 2 pairs, and 2 that are not paired. And if you have yours top and bottom or some other arrangement, that's fine. Because if you took that and just tipped it, right, atoms can move. They can twist around, and so you can't, and you can turn them on the paper too. You can't turn them on the screen though. Any questions about that?